Inside a neutron star lies one of the most extreme and fascinating environments in the known universe, a place where the laws of physics are pushed to their absolute limits and matter behaves in ways that are almost impossible to imagine. A neutron star is formed when a massive star exhausts its nuclear fuel and undergoes a supernova explosion, collapsing under its own gravity until protons and electrons are crushed together to form neutrons, resulting in an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. From the outside, a neutron star may appear small, typically only about 20 kilometers in diameter, yet it can contain more mass than our Sun, making it incredibly compact and powerful. As you move closer to its surface, gravity becomes overwhelmingly strong, about 100 billion times stronger than Earth's gravity, meaning that if you somehow stood on a neutron star, you would be instantly flattened into a thin layer of particles. The surface itself is believed to be a solid crust, composed of tightly packed atomic nuclei arranged in a lattice structure, somewhat like a crystal, but far denser and stronger than anything found on Earth. Beneath this crust, conditions become even more bizarre as you enter the inner layers where nuclei are squeezed so tightly that they begin to break apart, forming a strange phase of matter often referred to as nuclear pasta because its shapes resemble spaghetti, lasagna, and other complex structures created by the competition between nuclear forces and intense gravitational pressure. Deeper still, the star transitions into a superfluid of neutrons, a state of matter that flows without any resistance, allowing it to move in perfect, frictionless motion, while protons and electrons may form a superconducting fluid capable of conducting electricity with zero energy loss. This superfluid interior is responsible for some of the strange behaviors observed in neutron stars, such as sudden changes in their rotation speed, known as glitches, which occur when the superfluid core interacts with the crust in unpredictable ways. At even greater depths, scientists believe that matter may break down into its most fundamental components, possibly forming an exotic state known as quark matter, where neutrons dissolve into a soup of quarks, the basic building blocks of protons and neutrons, though this remains a topic of ongoing research and debate. The magnetic fields inside and around neutron stars are also extraordinarily powerful, trillions of times stronger than Earth's magnetic field, capable of distorting atoms and even affecting the structure of space itself, and in some cases, creating magnetars, a special type of neutron star with magnetic fields so intense that they can strip information from credit cards from thousands of kilometers away, if such a thing were even possible in practice. Time itself behaves differently near a neutron star due to its immense gravity, a consequence of Einstein's theory of general relativity, causing time to slow down relative to an observer far away, meaning that processes occurring on the star may appear slower from a distant perspective. Despite their extreme nature, neutron stars are also cosmic laboratories that help scientists understand fundamental physics, including the behavior of matter under extreme pressure, the nature of gravity, and the properties of nuclear forces. Observations of neutron stars, especially through X-ray and radio telescopes, have revealed pulsars, rapidly rotating neutron stars that emit beams of radiation from their magnetic poles, sweeping across space like cosmic lighthouses and allowing astronomers to measure their properties with incredible precision. Some neutron stars spin hundreds of times per second, making them among the fastest rotating objects in the universe, while others exist in binary systems where they orbit another star or even another neutron star, sometimes leading to spectacular collisions known as neutron-star mergers, which produce gravitational waves and heavy elements like gold and platinum, enriching the universe with the building blocks of planets and life. The study of neutron stars not only deepens our understanding of astrophysics, but also connects to broader questions about the origin and fate of the universe, as these objects represent the boundary between normal matter and the even more mysterious entities known as black holes. If a neutron star accumulates too much mass, it can collapse further into a black hole, an object with gravity so strong that not even light can escape, marking the ultimate limit of gravitational collapse. In many ways, neutron stars serve as a bridge between the familiar and the unknown, offering a glimpse into conditions that cannot be replicated on Earth and challenging scientists to develop new theories and technologies to understand them. As research continues with advanced observatories and space missions probing deeper into the cosmos, neutron stars remain one of the most intriguing and mysterious objects in the universe, embodying both the beauty and the brutality of cosmic evolution, and reminding us of the incredible forces at work in shaping the universe we live in.